So if you have the graph of a function and you want to find the limit of the function as x approaches a number. So suppose you want to find the limit of a function as x approaches c. Here is c on this graph, right? So basically what you want to do is you want to look immediately to the left of c, right? What y value is the graph approaching? It looks like it's approaching L. And you want to look immediately to the right of c. What y value is the graph approaching? It looks like it's approaching L. If the y values are approaching the same number from the left and right of that point, then we say there is a limit and the limit is L. Okay? Now, let's take a look at this function here. The limit, we want to find the limit of 4x plus 1 as x approaches -1 using a graph. Okay, so let's just graph 4x plus 1 for a minute, right? The y-intercept here is 4. I'm sorry, the y-intercept is 1. And we're going to go up 4 over 1. Okay, and you can, right, because that's the slope. And then you can put a couple more points, right? So from the center point, from the y-intercept, you can go down 4 to the right 1 and so on. Right? You could keep going up 4 over 1, up 4 over 1, and graph this. Okay? Did that? Let me do it again. Sorry. I know. I needed to have a ruler, but okay. All right. So what we needed to do here is we want to see the limit as x approaches -1. Right? So where is -1? That's right here. So in the beginning, I tell students you can draw like a dashed line at -1. We really stop doing this once we get a little bit more proficient with this. But if you draw a line, a vertical line at that x value at -1, look immediately to the left of that dashed line. What is the y value over there? Immediately to the left, it's like it's -3, right? And then immediately to the right, what is the y value? -3. And because the y value is approaching the same number, -3 and -3, from the left and the right, we say the limit as x approaches -1 of 4x plus 1 is equal to -3. Now, we do that using the graph, right? Just graphically. But we can also do that using a table of values. All right? So where is it that we're finding the limit? We want the limit as x approaches -1. So we make a table of values, and we put in that table values immediately next to -1. So on this side to the left, it's -1.001, -1.01, okay? And to the right, it's -0.999, -0.9, and so on. Okay, now we're going to plug those numbers into 4x plus 1. So I get -3.04, -3.004, okay? So look, as the x values are approaching -1, what are the y values approaching? -3. From the opposite side, here I get -2.996, -2.6. So as I approach -1, what are the y values approaching? -3. Okay? Now, did I ever plug in the value for -1? No, because that's not what I care about when I find the limit. I just want to know what y values are they approaching. And because from both sides it's approaching -3, again I say the limit is -3. Okay? So this is doing it graphically, this one numerically. All right. Yeah.
Why can't you just find what why can't you just plug in -1, 3,
because that's finding f of negative 1, right? That's finding the y value at x equals negative 1. A limit is not that. A limit is not finding the actual value. A limit is finding what y values are they approaching from both sides. They're two different things. And you'll see a little bit more right now. Yeah.
So for like a line, will it always be the same, like from the right and from the left, like for a linear equation?
Right, unless there was a discontinuity, right?
Okay.
Okay? Because some rational functions reduce to a linear function, and then Okay. So let's talk about what we were talking about, like a limit versus a value of a function. So take a look here. Take a look at this first one. Okay, look at how as you approach C, the y values are approaching L from the left and the right. Okay, so we say the limit of f of x as x approaches C is L. But what is the actual value at C? What is f of C? It's an open circle, so f of C is undefined. Do you see how they're completely different things? Now take a look at the next one. That's g of x. As x approaches C, okay, I'm approaching the same value from the left and the right. So the limit is L again. But what's g of C? What's the y value at C? There's an open circle here, but there is a closed dot over there. So g of C is n. Okay? The next one, take a look. As you approach C, the y values are approaching L from the left and the right, so the limit is L. But what's h of C? Also L. So do you see that? You know, the existence of a limit has nothing to do with the existence of the y value at that point. They are completely independent things. One doesn't affect the other. Okay, Mayan, question? I often do that, yes. Okay, so let's take a look at this one, and this goes back to what we were talking about earlier, okay? So, the limit as x approaches 4, x squared minus 16 over x minus 4. Now, you are all experienced pre-calc students by this point. You look at this function, and you know there is a discontinuity where?
4.
At x equals 4. It happens to be where we're finding the limit, right? So if f of x is x squared minus 16 over x minus 4, I need to graph this function now, right? This is x minus 4, x plus 4 over x minus 4. It reduces to x plus 4, which is what type of function? It's a linear function with the y-intercept of 4, and then you go up 1 over 1, but there is a discontinuity at x equals 4, right? There is a hole in the graph at x equals 4. Okay, so that is what this function looks like when you graph it, correct? Huh? We graphed this reduced to x plus 4. That's what we graphed, but it came from, see? So yes, it looks like a linear function, but it came from a rational function with a discontinuity of 4. So this line looks different than the previous line because this one has a removable discontinuity at x equals 4. Do you see that? So now we want the limit as x approaches 4. Okay, where is x equals 4? Right here. Now, immediately to the left of the line, what is the y value? Here, 8. Immediately to the right, what is the y value? 8. So we say the limit of x squared minus 16 over x minus 4 as x approaches 4 is 8. I don't care that there is a discontinuity there. That's not what the limit does. Okay, let's do it numerically. We're going to plug these values into here, x squared minus 16 over x minus 4. So I'm looking at as x approaches 4. So I pick numbers very, very close to it. 3.999, 3.99, 4.001, 4.01. Plug it in. I get 7.99, 7.999. Look, clearly it's approaching 8. On this side, I get 8.001, 8.01. Clearly, it's approaching 8 from here as well. I don't touch the x equals 4. That's not what a limit is about. Okay? And again, this confirms that the limit is equal to 8. Okay. Now, this one is graphically finding the limit. That one is finding the limit numerically. In calculus, there are always 3 ways to solve a problem. Graphically, you look at the graph and you analyze the graph. Numerically, just plug in values until you get your answer. Or analytically. We're going to do the first 2 today, and then section 2 is the other part. Okay? Now, I want to make the homework easy for you. Okay, you know, I had done this to show the graph. I don't even think I want to see the graph. Just use a calculator for the complicated function. Just use a calculator to graph the functions. Observe and give me the limit, okay? Estimate the limit by observation. Please do not make a table where it says, you know, function values, like support your answer numerically. Don't do that. So you don't have to do it. I don't even need to see the graphs. I'm going to trust that you're going to do them, okay? On the test, most of the time, like in real life, most of the time you'll be given the graph or whatever, okay? Just... So on the homework, we don't have to do the graphs? Not for the beginning ones. You only have to graph number 51. That's like a legit, like a word problem where you have to graph.
When we turn in our homework, the only thing you'll see is like...
Yeah.
Limits?
So, okay. So I want you to say, though, you know, the limit of the function as x approaches blah is equal to like -4, okay? Right. Okay. Now, let's talk about one-sided limits. Sometimes it's very practical, useful, important to just look at limits from one side, just the left side or just the right side. And we have special notation for that. So if we look at a limit just from the left side is where the negatives are, right? So we call it limit as x approaches c from the minus side. And if you look from the right side, this is what the notation is. Okay, so one is from the left side, one is from the right side. Okay, the official definition of a limit is this. A function has a limit as x approaches c if and only if the right hand and the left hand limits are equal. So, this means if there is a limit, the right hand and the left hand are equal, or the converse. If the right hand and the left hand limits are equal, then there is a limit. Okay? So this is very, very important here, this notation. The limit of f of x as x approaches c equals L means the limit as x approaches c plus is L, the limit as x approaches c minus is L. Do you guys know what this arrow, this double arrow means? Huh? It's the same as if and only if. And the notation, the shorthand for if and only if is IFF. Like that's not a typo. Okay, so what does if and only if mean? If and only if means the statement and the converse are true if you have if and only if. Okay? Okay? So, I mean, we can come up with like lots of statements like that. Okay. All right, so let's do some limits here. Okay, the limit of f of x as x approaches 0 from the negative side. If you want to do the, the dashed lines, you can, but as x approaches 0 from the left-hand side, so this is 0, immediately to the left of 0, where is the graph? At y equals 5, okay? So I say 5. Immediately to the right, where's the graph? 5. Now I'm asking you for the limit as x approaches 0. Because these are the same, this is also 5. Okay? Now the limit as x approaches -3. Here's -3. So immediately to the left, where's the y value? How much?
2, 3, 2, 0,
Or non-existent.
0. This dot here is just a pinpoint. Okay, that doesn't really have a dimension. Like, we make it big for you guys to see on the paper, but immediately to the left, where is the graph? Right here. It's at 0. Okay? Immediately to the right, where is it?
How is that to the left? Like, in my mind, that's on -3. How is that to the left?
Wait, what?
Isn't that on -3? Like the 0?
No. Because at -3, look, there's an open circle. So immediately to the left of it, you're like there. Okay? So this line is the -3. Like, immediately to the left of the line, you're at 0. So basically, like, when, y equals like -3.000001, when x equals that. Okay, -3 plus, where are we? 5. And as x approaches -3, look, these are not the same. So we say its D and E does not exist. Okay? Okay, now just for fun. Okay, we found for C the limit as x approaches 0. What's f of 0? 5. What's f of -3? 2. Okay?
So for 3 plus,
Uh-huh.
how is it? You take to the right of -3, right?
Uh-huh. So this is x equals 3. This one.
Yeah.
So immediately to the right of this, where's your graph? Immediately to the right. It's here. Don't say it's here, because this is like, it's just like a pinpoint.
It's not actually on the graph.
It's not actually like, yeah, it's like, it's so tiny. It's not to the left or to the right. It's just right there.
I see.
Oh,
Okay.
so it couldn't be a part of the limit. It's just.
It's just like a point. It's like a pinhole.
It's
You know how there's like,
Mhm.
yeah, you know how like there's when there's like a tiny pinhole that you, for the life of you, like on a balloon, that for the life of you, you cannot find, but you know there's like a hole and like air is leaking out. That's how big those points are. Okay, like even tinier than that. Okay, yeah.
Why do you look at the open circle on the top without the word on?
Okay, so it depends on where you're looking, right? If you look at x equals -3 from the minus side, from the left side, where is that? So this is x equals -3. Immediately to the left of this, where is the graph? Down here. So it's negative, so it's 0.
Why is it 0? I understand why it's 0 on the graph above. There, but when it goes down.
But it doesn't go down. You're looking literally here. Why is 0 there? Right, yeah. Okay, all right, let's move on. Okay, let's move on. For calculus, you have to be very, very proficient in drawing piecewise functions. So here I have a piecewise function that's partitioned at x equals 1. So the first thing you want to do is you want to plug in 1 into the first function. And when x equals 1, y is 3, right? So when x equals 1, y is 3, but it's an open circle. And then that's an x cubed plus 2. So it's a cubic function that has been shifted upwards by 2. So it looks like this. When x equals, okay, so now for the other one, you plug in 1 into the bottom function, and that gives you 3 again, but this time it's a closed circle. When you have closed on top of open, you just close this. And that's a linear function with a slope of 2. Okay, so that's what it looks like. So, the limit as x approaches 1 from the minus side. So this is 1. So immediately to the left of x equals 1, what's the y value? 3. How about immediately to the right? 3. And because these are the same, that's also 3. Okay?
I don't know why I thought it was 2.
You're looking too far to the left. Like, here is x equals 1, right? Like, just to the left, like stuck to the line immediately to the left.
Oh.
Don't go like a whole digit over. Imagine going like 0.000000001 over. Okay? All right. So here, this one, the graph is given to you as x equals -2. So here's -2. Okay? What's the limit as x approaches -2 from the minus side? What do you think? 3. What about from the positive side? -4, yeah. So this one is DNE. Okay, because they're not the same. Yeah. They're all 3 there. Okay. Now, okay, could we have done this without the graph? Yes, we could have. All you had to do for this one is plug this in here. So you get 3. For this one, you plug this in here, and you get y equals -4. Okay? So this is the left limit, the right limit, and because they're not the same, it's DNE. Okay? All right.
That's the 2 ways you solve by looking at the graph, or the 2 by plugging in.
Okay, next. Take a look at this one. Again, the function is given to you. We want to see what's happening at x equals 3. So here's x equals 3, right? Immediately to the left of 3, where's the y values going? Where are the y values going? Negative infinity. Immediately to the right, positive infinity. Are those the same? No, so it's DNE. Correct, but yes, it is a... Huh?
But we don't need that.
Correct. There is actually a vertical asymptote because the limit from the right and the left are the infinities. Okay? That's how you prove in calculus that it's a vertical asymptote. Okay, here we go. The limit as x approaches 0 from the negative side. Where are the y values going? Okay, positive side. So this one, negative infinity. Okay, now, where is negative infinity? If I told you to go and get in your spaceship and go and land at negative infinity, would you know where to go? No. You have no idea where to go. Because we don't know where that is, whenever you have infinity as an answer, we always also put /DNE. Now, notice how this DNE here has a different meaning than this DNE here, right? So when you're writing this, you cannot write just DNE without the infinity next to it, okay? All right, so here, look at the scale of this. This is sine of 1 over x. Look at the scale. It's going from -1 to 1, and that center part here is only from like negative 0.25 to 0.25. So what's happening here? Like the graph will come into this and then it'll start oscillating. And then, you know, it stops oscillating for a little bit. So the limit we want is as x approaches 0 from the negative side. What do you think the y value is there? No idea. No idea. So it's dne. Okay? Because we literally do not know. The oscillations there are so rapid that we really don't know. So do we know what the oscillations are doing as x approaches 0 from the positive side?
No.
Also no. So that's also dne. Well, that means this is also dne. Okay? All right. So now, we had a couple of situations where we saw that the limit does not exist. Let's put it all together. What are some reasons why a limit at a point will not exist? Okay. First one is f of x approaches different values from the left and right of c, right? So different values from the left and the right. So where in the examples that we just did we see that? A, B, C, D, or E?
B.
What do you guys think? B. B was the one, right? Do you see how it approached different values from the left and the right? So that's B. Okay. Another reason a limit will not exist is if f of x increases or decreases without bound. So the limit approaches infinity from the positive side, or it approaches infinity from the negative side. So where did we see that happening?
D.
D and what else?
And C.
And C.
Oh, okay. So, but you only need to write the like infinity slash dne if they're both approaching the same direction as infinity.
So anytime we have infinity, we put dne as well. Infinity slash dne. So I
But
could also
here,
do it
because they
here.
weren't even the same. We just wrote dne.
Oh, yes, 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 yes. And then if f of x oscillates between two fixed values, like which one?
Oh, the last one, E.
E. Okay? All right? Okay. Okay. So now, in all the examples that we did, we went, we were looking at the limit as x approaches a certain number, right? Limit as x approaches 0, 2, -4, and so on. Okay. Now, we're going to get away from those. We're going to go to the infinities. How do we look at limits at infinity? Well, let's take a look. Look at this one. What is the limit as x approaches infinity of this one? So as I go to positive infinity, what y value is the graph approaching?
Negative.
How much?
Negative.
-3. And as I approach negative infinity, what y value is it approaching? -3. Okay. How did we previously know this? What did we previously call this? It was 2 words, started with an end.
And B.
End behavior. This is what we know as end behavior. Okay? It's also what happens, it's also like the limit as x approaches infinity. Okay. Okay, look at this one. This is our very own, our trusted and loved sine of x. So what happens as x approaches infinity? What's the y value going to approach as x approaches infinity?
In between.
Does not exist because you don't know. Because, okay, so if I continue this, okay, it's going to keep going up and down, right? So how do I know where infinity is? Is this infinity? Or is this at infinity? Or maybe this? Or maybe this? Maybe here's infinity. Okay, we're really at infinity now. I don't know, right? So dne.
So, but it's not linked with that.
No, because you don't know where infinity is. Like, you can't say, show me where this is at infinity, because infinity is like, it's ever expanding. We don't know.
But is it like where y?
Right? but when x, when the universe stops, right? That's where infinity is supposed to be. But where is that? We don't know. Because however out you go, you could always go another step after that.
No, yeah.
So it never ends.
But I think I was just confused because I was thinking why.
Yeah. Right. It's here because you don't know if it's gonna be here, or where.
Yeah. But the graph above, couldn't it also change and then if you extend further out?
Yeah, I mean, yeah, but we know the function too, and look, the trend looks like it's very clearly flatlining, and usually there are very few surprises, far out there. All the action usually happens here, and then it it's like when a person gets old, it's very little spontaneity,
Wait,
you know.
It's only flat, when it's flat, then you have a limit.
Yeah. Yes and no.
See how it,
Yeah.
for the side graph, it still stops at or I don't know if that's -1, but
It could also have been. Oh, look at this one. Look at this one here. The limit as x approaches infinity, this one would have worked, right? Because there is a trend, it's going up to positive infinity. So you know which way it's headed. But for the one that's oscillating, all you know is it's going to be somewhere between 1 and -1, but you don't know exactly where. Okay, this next one, this is perhaps, this family of functions is perhaps my favorite family of functions. Because, take a look. Suppose you graph y equals e to the x and y equals negative e to the x, right? What would that look like? Well, here's e to the x and here's negative e to the x, right? Now, what does sine x look like? Well, we just saw sine x looks like this. But now if I multiplied the two of them together, then at each point, right, then the e to the x's make a little boundary, right, for the sine, and it makes the sine looks like that. It is one of the most beautiful things ever. And a lot of things for example, when you have damping in circuits, when the circuit signal starts to decrease and so on, this is this is what it is. So what happens here as the limit as x approaches infinity? You don't know. It's dne because it's just oscillating like mad.
is the other one 0?
Is the other one 0?
Yes.
Yes, it's 0. Clearly you see that it's dying out to 0. Okay? Okay, and that is section 1.